Hi, everyone. This is another 5 Minutes Coffee Talk episode. This series is to explain the frontier ML concept or technology in academic and industrial world in 5 minutes. This series is designed by Paul and brought to you by Yidu AI. The voice in the video comes from NLP technology. Later on, maybe you will hear different voice in the series if we change the training data. Today, we talk about the model aggregation strategies for federated learning. We first discuss one of the two questions left in last video. Since the second one is the main topic of this video, some of us may think about one natural question. Since we need to handle the data privacy problem, why not we just deploy a model to user's device and then let the user to train their personalized model with their own data? However, there are some constraints in real life. First, personalized user data usually is not enough for training a better model. Also, individual user cannot take the advantage of other users' meaningful data without communication to the server. Of course, for some user who generate quality data frequently, they may get a good personalized model even without communication with server. But in the Pareto efficiency sense, the communication between user device and server is the must. Before we describe the model aggregation strategy, we introduce some notations and stochastic gradient descent algorithm, which is the most popular optimization algorithm in current machine learning world. Assume we have k devices. Each device has nk data. The optimization in federated learning could be written as this. Here, J is the loss function such as cross entropy. Stochastic gradient descent is the most popular optimization algorithm in machine learning. Here, we cannot explain it in details, but we introduce the key idea. The key idea for iterative optimization algorithm minimize the objective loss function is finding a descent direction d and a suitable step length alpha. It is well known that the negative gradient is the descent direction. Moreover, the auto-differentiation mechanism in many popular machine learning framework makes the gradient of the loss function for machine learning model accessible. On the other hand, due to the huge dataset, if we compute the full gradient of the loss function, one step update is too expensive. That's the motivation for stochastic gradient descent. Just randomly sample a batch of the whole dataset when we do one step of update. However, some default assumptions in classic stochastic gradient descent, especially in distributed setting, are not true for federated learning. Here, we list 4 important challenges in optimization for federated learning. Among them, the most important 2 are data are not independently identically distributed. That because personalized data in each user's device may not follow the distribution among population. The key problem caused by this is that the expectation of the user data is not equal to the expectation of the population data, which contradicts to the assumption for the standard convergence analysis framework. The second one is data are massively distributed. In standard distributed machine learning settings, we usually assume that number of data generated by each client user is much larger than the number of clients. But the situation in federated learning is opposite, which in other words, may indicate the data in each device is biased. With the concepts and discussion until now, we can start to discuss the shared model update strategy, one very natural idea, which can apply the stochastic gradient descent algorithm directly for federated learning. We can do like this. Each step, randomly choose a client with the most updated model. Get it locally computed gradient. Update the model for one step with the gradient. Then, deploy this new model to some randomly selected clients. We can see that this is the SGD strategy. The computation is very efficient since all the computation can be done in user's device. However, we know that for this algorithm, to get a reasonably good model need a lot of rounds. But each round needs the communication between devices and server, which is quite expensive. Another drawback of this idea, in my opinion, comes from the non-IID property of federated learning. You can understand it in this way. Each time, the data you obtain to update the model are not from the real population distribution, but from user's distribution, which might cause some problems. So, is there any better idea rather than the naive SGD? There is one principle in statistics. I am kidding. If you do not know how to get a better idea, just averaging all of them. If doesn't work, try to weighted averaging them. This is the idea behind federated averaging strategy. Each time we sample a group of clients, Get their updated model. Each model may be trained multiple steps locally to server. Then weighted averaging the model parameter, proportional to the number of data. The details of the federated averaging algorithm is shown here. We can see, basically, the algorithm is to weighted averaging the randomly selected client's locally updated model parameters proportional to the number of user data. Here are some numerical experiments results comparison between FedSGD and federated averaging. Although I think comparing these two algorithms respect to communication rounds is a little bit unfair. But we can basically see that federated averaging algorithm performs better. Some authors regard this strategy as some kind of model ensemble. For me, I prefer to thinking about this as a better strategy for non-IID data. The motivation for me to think in this way comes from the idea of mixture Gaussian. We know that the real distribution we try to learn is the population distribution. Although each individual distribution may not be the population distribution, but the mixture of them may be closer. Since we already observed the outperformance of the federated averaging algorithm, can we prove the convergence of this algorithm on the non-IID setting? We will try to have some discussion on this for next video. Thanks for watching. If you like our content, please follow us. If you have any comments or feedbacks, please leave a message below. Your feedbacks will help us a lot for creating better contents.